So now we're going to look at the neighborhood relationships between pixels and use that as a starting point to be able to um, uh, groups of pixels that are within an image, describe them as being a group of pixels, and we will see that that can be done to take the next step up from creating a binary image. So let's assume, first of all, that we have obtained a binary image as a result of some simple decision process on a grayscale or a color version of an image. So the next step in these in sort of doing some processing is to think about neighborhood relationships amongst pixels that share the same intensity of pixel, that is either be it a 0 or a 1, or possibly also pixels that within a neighborhood contain a difference between either a totally homogeneous in all being 1, or perhaps there is a neighborhood pixel in there in some sense that contains a value that's different from the majority. So we first have to describe what we mean by a neighborhood of pixels. And in particular, we also need to look at the notion of something called connectivity. So the nice thing about binary images is that once you've got rid of the complexities associated with having different grayscales or different colors assigned to pixels, you can focus on spatial relationships because you've only got two colors to think about, or two values to think about within your within any group of pixels you consider. So if we are at some location in the image, so some pixel location that we denote by P, with coordinates, this should be, so this should say coordinates. So let's just write coords. So with coordinates Mn, then we can think about, we tend to think about the 4 connected neighbors, or the 8 connected neighbors, or the diagonally connected neighbors of that pixel P. So this connectivity thing is a very useful concept because it then allows us, so before I move on to this, let's look at this diagonal and 4 connected and 8 connected neighborhood of pixels. So our central pixel is P in the region here. So if we talk about the 4 connected neighbors of P, we are usually referring to the 4 pixels that go out vertically upwards, directly vertically upwards, vertically downwards, horizontally to the left, and horizontally to the right. So we're moving in sort of steps of 1, if you like, along one row. So 1 row up, 1 row down, 1 column to the left, 1 column to the right. But in all cases, we only change the row coordinate or the column coordinate in getting to the neighbor. We can also consider cases in which we change both the row and the column coordinates to get to neighbors, in both cases by 1. And so this would be what these 4 pixels here would be called the diagonally connected neighbors of this central pixel here. We can also talk about the 8 connected neighbors, in which we consider all the pixels that lie within a little 3x3 block, with the pixel P being at the center of that 3x3 block. So these are the 3 principal types of connectivity that we meet. And if we consider any 2 pixels, P and Q, then the notion of connectivity usually refers to the fact that they are sharing the same grayscale value. Normally, there are cases where we don't care about the so sometimes we talk about when we talk about connectivity, we pay attention to the the intensities of the 4 connected or 8 connected neighbors. In other cases, we don't. So the algorithms will use both versions of this, either, and just by looking at the context of what the algorithm is trying to do, you can kind of work out what the intention is of talking about 4 or 8 connected neighbors. But generally speaking, you're just talking about these spatial relationships. So Q being in amongst the 4 neighbors of P would be one of those 4, not diagonally, so would be one of these 4 guys here, right? The 8 connectivity would be Q being a second pixel Q relative to P being somewhere amongst these 8 neighbors here. And for the ND connectivity then, so you could write a third equation here, or expression here for the ND connectivity of P. Okay, so one thing that we need to be careful with, though, is this notion of distance, because if we come back to this case here, we've got 4 connected neighbors that are like this, and 4 connected neighbors that are like this. They're called diagonally connected neighbors. Do we treat these pixels here in these corners as being equivalent to these pixels? Well, clearly they're not. They're different pixels. And the obvious thing that's happened, if we contrast this group of 4 with this group of 4, is that this group of 4, we change 2 coordinates, so both the row and the column coordinate, to get to one of the diagonal neighbors. And in doing that, we're reflecting the fact that we've actually got a distance that's also greater if you were to use a Euclidean distance of measure between the center pixel and one of its diagonally connected neighbors versus one of its 4 connected neighbors. So this would be a distance of 1. Let's say if we use Euclidean distance, these 2 would be a distance apart of 1. But these 2 would be a distance apart of root 2. So 1, square root of 1 plus 1. Okay. So it also, however, brings to mind the idea that we should also think about how we define a distance when we're dealing with something like a discrete grid. And there are very good cases for not using a Euclidean distance, particularly in describing algorithms which try to draw geometric shapes on screen. And it turns out that some algorithms, despite the fact that, of course, you'd want geometry on screen to reflect in some way geometry in the real world, there are cases in which at the algorithm level, you want to actually determine whether 2 points are nearer in a row direction or perhaps in a column direction. And this changes the way that you write the algorithm. So given that and all other things considered, it's useful to think about a series of distances that we can describe to measure in some sense, the spacing. I come back to distance to measure the distance between 2 pixels. So distance measures, how we define distance measures, becomes something that is worth devoting some time to. So a distance metric, d, can be described as being a metric if it has a few properties. So to measure the distance between 2 pixels p and q, we introduce the idea, the more general notion of a metric. And the properties of a metric are such that if we take 2 pixels p and q, then for whatever distance metric we propose, we would like that the distance between, so d applied to where d is the metric, so d between p and q is greater than or equal to 0, unless p is equal to q. So that's the equality condition there, equality condition when p is equal to q. We would want d between p and q to be equal to d between q and p, so that the ordering of which pixel we start at doesn't matter. And then if we introduce a third location indicated by z, then the distance metric between p and z should be less than or equal to the distance metric between p and q plus the distance metric between q and z. So this is a sort of way of abstracting the notion of distance. And once you've done that, you can then come up with a bunch of other distance metrics. So The Euclidean distance is the one that we've already described, and so you would use MP minus MQ, so find the difference between the row coordinates, square that, add that to the square of the distance between the column coordinates, NP minus NQ squared. Yeah, I think I said squared twice there, and then find the square root of all of that. The D4 city block distance is the sum of the absolute difference in the row, the row numbers between pixel P and Q, plus the absolute difference between the column coordinates of P and Q. And then the D8 or chessboard distance would be the maximum of MP minus Q, so the difference in the row coordinates, or absolute value of the distance between the row coordinates, or absolute value of the difference between the column coordinates. Okay, so it's the max of either of those two. So these are three metrics that you will find commonly used in describing image processing algorithms. Now, once we've got to the notion of connectivity and we can distinguish between 4 and 8 connected, then we can move on to looking at connected component labeling. And so, first of all, I'm going to start by showing you what the endpoint of connected component labeling gives you, because it's quite interesting and a very simple and elegant algorithm. So let me just shift myself up into view here, and if this is seemingly very small, so let's zoom this out a bit. Okay, I think that will do the trick. Position myself in there. It's weird to kind of just scroll yourself around on screen. Okay, so let's now have a look at this this demonstration here. So what I'm doing here is I'm in this little example here. So by the way, you're going to be doing something very similar in your P's on Desk practical, which comes up after you've done the color map practical. So first of all, we're loading an image that contains rice grain, so it's rice.png. What I'm doing here is just opening the image and then displaying it as a grayscale image. Here, what I've done is to apply a thresholding operation. So I know already from sort of prior experience that that's a good threshold to use for this example. So after I apply this, xb, large x, little b, as an image, becomes looks like this thing. It's not a perfect job of separating rice grains from background, but the point to make here is that now we've just applied a simple thresholding, and we now have the value of 1 indicating pixels that belong to a rice grain, and that value is the same for all rice grain pixels, and we have a value of 0 for all pixels that are not a rice grain. Okay, very simple. We've missed some rice grains down below here, but that doesn't matter. We learn how to deal with that problem later on. So the next bit of processing that's done here is to load up an algorithm that's called, well, it's actually a connected component labeling algorithm, just as I describe in the notes, and I will explain how that works once we see, for example, what the result looks like. And the algorithm that I would recommend using is one from scikit-image. It's the scikit-image measure module, and it's called label, which is a pretty sensible name for it. In addition to that, if you were using MATLAB, for example, there's something called BW label, which would be the equivalent operator in MATLAB. Well, kind of equivalent. They're not exactly the same. So what I've done here is to just apply the labeling process, connected component labeling, to the binary image xb. And the result of that, and I'm now displaying this with a color map that's jet to make this a bit easier to perceive, is now this. Okay. Now, you need to interpret this, you need to remember that when I display an image as a color map image, so I'm using a particular funky color map here. In fact, let's just put the color bar on. I think it's plt.colorbar. So let's just drop the color bar on there. Oh right, sorry, I need to start this properly, so let's just run through these things here. Okay, this is from the previous demonstration I've done earlier on. Okay, there we go. So, and now we can, so this should apply the connected components labeling algorithm, and now we can plot it. And there we go. So there's a color bar. So the values here inside the image are going from 0 up to, I don't know, somewhere around 110, 115, somewhere around there. And so each of these rice grains now has a non-zero value like we had up here, but now each distinct rice grain has a distinct value. So in other words, all the pixels inside this rice grain I'm pointing to here, for example, have a value that's somewhere along here. So it's probably somewhere around 32 or so. All the pixels in this rice grain have a value somewhere around here. All the pixels in this rice grain have a value somewhere around 60. So we've got values in the rice grain in the image now, where previously we had ones for all the pixels that belong to rice grains. Now we have a distinct non-zero value for every pixel in each distinct rice grain. So it means once we've got that, we can now do something like this. We can say, okay, let's take our labeled image, X labeled. So by the way, if you want to see what this looks like, we can just have a look at, I guess, at X label, a few samples from X label, just so you can see what they look like. Maybe let's drop it into here to make that point crystal clear. Oh no, if I do that, it's just going to plot the image, so I'm not going to do that. We'd have to get at the values in the array to do that. So you'll see that when you get onto the practical. So it'll become easier when we get into the practical. So, because, what I'm saying is that if I were to do this, just try to show you the values in the array. This is the stupidity of object-oriented programming, right? X labeled. If I were doing this in MATLAB, MATLAB would show us the array. If I do this in Python, just using the variable X labeled, it's actually going to display the image, which is useless because I can't actually. Oh, actually, it's not doing that. How hilarious. Okay, so let's have a look at a few values in there. Let's say, 30 to 50. No idea if that's right, but let's have a quick look. There we go. So you can see. Although it's kind of expanded beyond the size of the display, convenient display. Let's go from 25 or so up to, yeah. So it's actually the columns we want to change. So let's go 35 to 50. Let's make it a bit smaller. Let's see what that looks like. There you go. So you can see sort of an edge of a rice grain there, and that rice grain has values that are all 16. And then you can see another little chunk, a little line of pixels here that belong to another rice grain, which has its pixels are all labeled with 17. Okay, so isn't that nifty? Well, it's even niftier than that, because what I can do is I can actually go in and pick up rice grain 25, for example. So if I did this, so this is now a Boolean operation that says set to, so in shorthand for this line of code here, make a variable called arg25, which satisfies the following condition. So X labeled, in other words, the value of X labeled must be equal to 25. So if that condition is true, then arg25 will have a value of 1. And if that is not true, then arg25 at that location will have a value of 0. So arg25 is effectively a Boolean variable, but we can display it and just display RG25 and see what it looks like. And so that's it. So the size of RG25 is the same as the size of X labeled. So that this is a nice shortcut for running through every pixel in the image and doing a test to see if its value is equal to 25 or not. Okay, so very nifty. You can also do this in MATLAB. It works really nicely. So that's rice grain 25. We can also look at rice grain 12. So let's also do rice grain 12. So just to be super lazy, I'll just copy that and change this to 12 and change that to 12 and run that. So, and then if we look at RG12, then we can, we'll see that it is another rice grain that's, oops, sorry, that should be 12. That's being super lazy. There you go. That's rice grain 12. That's rice grain 25. Okay. And another nifty thing about this is that you can, because these things will, by definition, not overlap, because we've applied this something called connected components labeling. We can also do the following, which is that we can look at, for example, we can do RG12 plus RG25, and it'll be that. It'll be those two rice grains. Okay, so this algorithm is really nifty. It's called connected components labeling. So let's see how it works. And so to understand how this works, we're going to start by looking at a very simple example. Now, one thing to be ultra careful with here is that we've got here on the left hand side, so figure D is end result. So this is the end result. Sorry, I'm writing without my tablet again, since it's miscalibrated. So that's the end result for 4 connected. Okay, so this is 4 connected. And on this side, we have an end result for 8 connected. So E, figure E here, does not follow after figure D. These are 2 different end results. So this is end result if we use a definition of 8 connected. 8 connected. So 8 connected. Okay, so now let's look at how so we're going to come back to this this difference at the end. Okay, so let's make a second line there to make sure that we don't think that E comes from D. It doesn't. E comes from starting back at the beginning and running through the algorithm with a different notion of connectivity. So let's start by running through to see how we get to this 4 connected result first of all. So you start off, here's our binary image. It's a nice simple binary image which doesn't have many pixels in it. And we've got values of 1 and values of 0. So the first step in connected component labeling, which by the way you can find the algorithm in the full set of lecture notes. So please go through and read that algorithm, make sure you understand how it works. Once I've run through the algorithm with you, you should be able to see that actually it's pretty easy to understand how this fits together. So the way this works is that we start off by assigning a unique non-zero label to each of the pixels within our which have a value of 1 in this image. And so the first pixel stays as a 1. The second pixel we label as a 2. The third non-zero pixel we label as a 3. The fourth as a 4. The fifth as a 5, etc. So what we've done here is assign a unique label to every pixel that is non-zero. Okay, that's the first step. Very simple initialization step. The next step is, oh, and by the way, in doing this, what we typically do is we start from the top left of the binary image and run across to the top right along the first row. Then we go to the second row and repeat the process. Third row, repeat the process. So we call this scanning in a raster fashion. R-A-S-T-E-R, raster fashion. So we scroll back and forth, left to right in a raster fashion, from top left to bottom right. Once we've then assigned a unique label, again going left to right, which is why these values are increasing 1, 2, 3, then to 4, 5, 6, 7, 8, 9, 10, 11. That's why they're increasing this way, because we're going top left, bottom right in a raster fashion. The next step is to work inside this image using what's called an in-place algorithm, which means we go through this image. Don't create a new image yet. Just work on this image and change the values in this image as we go. Again, top left to bottom right. But as we go along, we change the pixel values according to the following simple rule. So we consider first only the non-zero pixels, so 1, 2, 3, 4, 5, 6, etc. For each of these, again moving in the top left to bottom right, we consider the pixel and its 4 nearest non-zero connected neighbors, and we replace the central pixel, let's call it P, with the minimum of the non-zero 4 connected values within its 4 connected neighborhood, including itself. So here we're using N4, where N4 is, so depending on how you define N4 is whether N4 includes the central pixel itself or whether N4 is the 4 connected neighbors of the central pixel, then you would have to adjust your notation slightly. So let's say we use, so in this case we need to consider the pixel itself. So so the 4 connected neighbors that are non-zero, including itself, will give us the values of 1, 2, and 4, if we consider those 4 connected neighbors that are not 0, because we don't consider 0, and 5 is not in the 4 connected pixels of this, so we don't consider 5 either. So the pixels we're considering are 1, 2, and 4. There's nothing to the left of us, so we don't need to consider them. So out of pixels 1, 2, and 4, we now replace this pixel with the minimum of those amongst those 3 values, that set of 3 values. So the minimum of 1, 2, and 4 is 1, which is the pixel value itself. So this pixel remains unchanged, or if you like, you replace it with the value 1. Doesn't make a difference. You then move, again, raster format, left to right, to the next pixel. Okay. So let's say that at the end of the first, considering this pixel, that stays as a 1. When we get to this pixel and we consider its 4 connected non-zero nearest neighbors, that's out. We consider this, but this one is now, well, this is 1, was before. That value is 3, that value is 5, and the pixel itself is 2. So now we take this set of values, 1, 2, 3, and 5, and we replace this value with the minimum of those 4. The minimum of those 4 is 1, so that gets replaced with a 1. Okay, so there's no longer a 2. Okay, then we move to the next pixel and repeat the process. So 4 connected neighbors, including itself, 1, 3, and 6, non-zero connected neighbors, 1, 3, and 6. So minimum of those is 1, so this gets replaced with a 1. So that becomes a 1. Okay, so now we now have 1, 1, 1. Continue moving along, then drop to the next line. So 4 compared with its 4 nearest neighbors, got a 1 there. So 1, 4, and 5 will be the 4 connected neighbor values. So we replace this with a 1, the minimum of those. This guy also gets replaced with a 1, and this guy gets replaced also with a 1. Okay, so at the end of that process, these, when we get to this point, let's say, all of these pixels are replaced with 1s. When we get to this pixel, so 0, 0, 0 do nothing. When we get to this pixel, this has no 4 connected neighbors, so no non-zero 4 connected neighbors. So this stays as 7. And this here, the minimum of the 4 connected neighbors of the 8 is the 8 itself, so that stays as 8. That one, 9, becomes replaced with 8. So that becomes an 8. And so on, right? So at the end of that process, so that becomes an 8, and that becomes an 8. So let's scratch that. Sorry. Scratch that. So these become, this is the result of that process. Once we've done top left to bottom right, till we get to the end, we then repeat that process going bottom right to top left. Okay. In this case, nothing will change, but it is, you can't generally assume that. So if you would like to see cases of structures, binary structures or binary regions, where the backward pass makes a difference, have a look at a couple of the past exam papers which contain structures, binary image structures, where the backward pass changes things in the intermediate stage of the connected components labeling process. Okay, so but what we do is we continue running a forward and backward pass over and over again until there is no change between a complete forward and a complete backward pass. In other words, a complete backward pass is the same as the forward pass that preceded it, or a complete forward pass followed by a backward pass is the same as the complete cycle of forward and backward passes from a previous iteration. So think about that carefully to make sure you understand the point at which you stop. There are also criteria that you can use to make that more efficient, but generally speaking, that would be the criteria to use. So no change in the labeling. However, we still aren't finished. So once we've got this result, so there's no further change through forward and backward passes in doing this replacement, in-place replacement, what we next do is we go through the image and we replace each non-zero pixel by the order of its number in the sequence of unique numbers that are found in the image. So, for example, if I look at this result here, which I consider to be the final result before relabeling, a relabeling process, there are 3 unique non-zero labels in the image. There's 1s, there's 7s, and there's 8s. So what we then do is we recognize that 1 is the first label, and so we replace 1 with 1, so the 1 stays unchanged. We recognize that 7 is the second label, second non-zero label, so we replace the 7 with 2, and then we replace the 8 with 3, because 8 is the third unique label we have within our image. So there are nice routines in most programming languages and operating system libraries to do that. So the command unique is one that you find in MATLAB, and there's something that's you can find in various, in Python I think has a unique function as well. You look at a bunch of integers and just pull up the unique values from that bunch of integers. I forget exactly what the command is, but it's you can look it up. So at the end of that process, we relabel these non-zero pixels with 1, 2, and 3, and so the biggest value that we get at the end of connected component labeling in the image also tells us about the number of unique regions we have in that image. Now this result here gives us 3 distinct regions because we've used 4 connected labeling. However, if you were to redo this process, but instead of using a 4 connected definition of neighborhoods, you use an 8 connected definition of neighborhoods, then when you get to this point, you will find that, actually it's this point, this pixel will be the same, will be considered to be connected to that pixel. And therefore, when you get to this stage in the algorithm, that 7, if you consider the 8 connected non-zero values in its in its neighborhood, then you get 1, 7, and 8. And the minimum of those is 1. So 7 will be flipped to a 1. And also when you get onto the 8 and all the pixels beyond, they will also be flipped to a 7, because the 8 will be flipped to a 7, the 9 will be flipped to a 7, the 10 will be flipped to a 7, and the 11 will also be flipped to a 7. So the end result of that would be just one region, all labeled with, I'm sorry, I said 7. They'll be labeled with 1. So the 7 becomes a 1, the 8 becomes a 1, the 9 becomes a 1, the 10 becomes a 1, and the 11 becomes a 1. Sorry. So everything gets the same label throughout this region. So you get that, which looks really unremarkable because it looks the same as that. But what this tells you is, because it's at the end of the process, you now have one big region in this image according to an 8-connected notion of connectedness. And so this clump of pixels down here is considered connected to this clump of pixels up here because of that diagonal connected pixel over here. Okay? So that's the end result of an 8-connected labeling of this image. Okay? So make sure you understand that carefully from that explanation. Okay, so the final point to note about this is that this iterative section of the algorithm is performed in place. So for a finite size image, convergence is guaranteed, but you do need the multiple directional passes, so top down to bottom right, theoretically to speed the convergence. And practically, I have found cases where with a limit on the number of iterations, the result of the labeling was incorrect unless the backward pass is included. And there are some examples of these. Don't assume that the backward passes are necessary. Have a look at your past exam papers where there's two years where I give something and the backward pass is absolutely necessary.